All right, welcome to our third set of notes for 4-7. In this section, we are going to focus a lot on oblique asymptotes, or what are also known as slant asymptotes. Now notice on our examples, you're going to see it in example 1, you'll see it also in example 2 and example 3. The degree of the numerator is greater than the degree of the denominator, so things change here. All right, for example, there is no horizontal asymptote. That's something that we learned. All right, so, but a lot of the other things that we've been doing stay. All right, let's go ahead and dive into example number 1. So like we've been doing with our other examples, let's go ahead and look at our intercepts, our wholes, etc. So the numerator, I am going to factor to x minus 4 times x plus 1. And the reason I did this was to see if we had any wholes, but since the denominator and the numerator do not cancel out, so there are none. Okay, all right, our x-intercepts, well, remember that we're going to set our numerator equal to 0, and if we do that, we have an x equal to -1 and an x equal to 4. Y-intercepts, I'm going to go back and look at the original. If I plug in 0 for all my x's, I'm going to be left with a -4/3. Vertical asymptote, well, we see that we're going to have one at x equal to -3. All right, horizontal asymptote. It's not going to be a horizontal asymptote. It is going to be what we call OA for an oblique asymptote. Now this is how we find it. We are going to use long division in order to find the value of our oblique asymptote. Now, why long division versus synthetic? Well, not all of our problems are going to be in the form of x minus a like they are in example 1. Notice that the denominator over here is x squared minus 1, which means you can't use synthetic division. You have to use long division. So we might as well just get in the habit of using long division for all of them. All right, just to give you a heads up, just to save you some time and to shorten the video a little bit here, I'm going to pause the video, I am going to do the long division, and then I'll start it up again and it's going to appear. All right, so I did the long division, and this is what I came up with. All right, what you need to know is that our oblique asymptote is going to occur at y equal to x minus 6. Basically, our oblique asymptote comes from our quotient that we get from our long division. Now, the big question that you're going to ask about is probably, well, what about the remainder? The remainder does not affect our oblique asymptote. All we need is the quotient. And so it's going to be a line, and that's why it's also called sometimes a slant asymptote, because as you can see, it's going to end up being a linear equation. All right, let's go ahead and graph our results. If I graph my vertical asymptote at x equal to -3, I get the following situation. All right, if I graph my oblique or slant asymptote at y equal to -6, I've got the following situation. Remember that it has a slope of 1 and a y-intercept of -6. Next, I am going to graph my x-intercepts. So I've got an x-intercept at -1. I've got an x-intercept at 4. I also have a y-intercept at -4/3. All right, these 3 points alone give me a good idea of what's occurring with my graph, that it is going to come down, pass through here, and then continue up. Don't forget that we also have a graph that is occurring on the other side of our vertical asymptote. I am not going to graph the other part just because if I plug in a x value of -4, I'm going to get a y value of -24, so it's way off of the graph. So based upon the picture that we have, this is good enough. All right, let's look at example number 2. All right, with this one, I am going to start by factoring. I like to just do that just to see if there are any holes. And by using the difference of two cubes, I have x minus 2 times x squared plus 2x plus 4. Remember your concept of SOAP. Okay, and then on the denominator, I have x minus 1 times x plus 1. All right, let's go ahead and fill out our chart for our information. All right, I do not see any situations in which we're going to have a hole. If I look at, so this is none, x-intercepts, well, we're going to have 1 at 2. You are probably asking, well, what about this part right here? If you were to do the quadratic formula, you're going to end up with an I. So they're going to be imaginary x-intercepts, which is a completely different graph. So we do not have to worry about graphing those. All right, and then we can move on to our y-intercepts. Notice if we plug in 0 for x, we would end up with a negative 8 over negative 1. So we're going to have a y-intercept at 8. Vertical asymptotes, we can see that we're going to have 1 at x equal to negative 1 and x equal to 1. Since the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote, but instead we do have an oblique asymptote. All right, and again, I'm going to pause the video and I am going to show the long division and then come back and we'll finish with the graph. All right, after completing the long division, this is what I am left with. The x squared minus 1 cannot go into this, so this is my remainder. And since this is my quotient, we can say that we have an oblique asymptote occurring at y equal to x, which basically is going to go from one corner of the graph all the way through. Okay, we have our vertical asymptote occurring at negative 1, and then we also have one occurring at positive 1. So now if I go and graph some of my points here, I have an x-intercept occurring at 2. I've got a y-intercept occurring at 8. And so now I can go ahead and find some more points for my graph. I know when x is equal to 3, I'm going to have like a 2.375. Okay, and so I have a graph that is doing this, passing through those points. Up here, I have a very little parabola that is in between my two asymptotes. And then if I go and plug in some of the x values that are over here, like x equal to negative 2, I am going to get a negative 5 and a third, which is all the way down here. And so now I know that I have a graph that is occurring like this. I'm going to pause the video for a second, and I'm going to insert a couple of pictures and just kind of show you, you know, in terms of our calculator, what this all looks like as well, just to give it a little bit of a clearer picture. All right, the top graph that you see up here is the one that does not have the oblique asymptote on it, and then the one down here does have the oblique asymptote, and as you can see, both of our graphs are approaching the asymptote. All right, let's go ahead and look at our third example. All right, if we take a look at our third example, I have it written here in standard form as well as written in factored form. So we can see right off the bat that we're not going to have any holes. We can see that we have x-intercepts that are going to occur at 3, at 1, and at negative 2. And the big thing that I want you to notice is because of the x plus 2 to the second power, that this here is going to be a situation in which it is a touch, which means that our parabola is going to come down and touch at negative 2, or it is going to come up and touch at negative 2. We'll have to see that when we get to our graphing. Our y-intercept is going to occur at 12/16, which we can simplify down to 3/4. Vertical asymptotes, we could see that we have one at x equal to negative 1 and x equal to negative 4. We're not going to have a horizontal asymptote. We're going to have an oblique asymptote. And like I've done in the past, I am going to pause the video and show the long division, and then I'll start it up again. Okay, after doing the long division, I got the following result. You don't necessarily have to write down the long division part. Hopefully you know how to do long division by now. I just want you to show the work that, or see the work that's involved, and see that our quotient is x minus 9. So that means that we're going to have an oblique asymptote at y equal to x minus 9. Okay, and this is our remainder because x cubed can't go into an x squared. This part I'm going to leave for your teachers to talk about in class. There's something that we can do with that for now. I'm just going to move on to our graph. So we know that we have asymptotes occurring at x equal to -4 and x equal to -1. We also know that we have an oblique occurring with a y-intercept of -9 and a slope of -1, or +1, sorry. So you've got the following. We also know our y-intercepts and our x-intercepts. So there's one that is occurring at 3/4. There's one that is occurring at 1, and there's one that is occurring at 3. So our graph must be coming down, crossing the y-axis, crossing the x-axis, coming back, crossing the x-axis, and then shooting up towards our our oblique asymptote. All right, in between our two asymptotes here, we know that we have a touch that is occurring here. So one of the things that I can do is I can plug in -3 into my graph. And when I plug -3 in, I get -12 for a y value. That tells me that my parabola must be coming up, touching here, and then shooting right back down. Okay, and you will see that if we were to go further, that our oblique asymptote would actually cross these two parts. Reminder that graphs can cross horizontal or oblique asymptotes, they just can't cross vertical ones. And then on the other side of our oblique, we're going to have one, a part of our graph occurring all the way down here, but again, it doesn't show up on our graph. So what I am going to do though is I'm going to pause the video and I'm going to show you what it looks like on our graphing calculator in two different ways. Alright, as you can see here, this is similar to what we graphed. Alright, and then now I'm going to show you what it looks like with our asymptote and with it zoomed out. Alright, so this new picture that I inserted shows the red line for the oblique asymptote. You can see that middle part of our parabola is crossing it. Okay, and then you can see this part of our graph all the way down here, which is too far off the graph that I have provided. Alright, so hopefully this gives you an idea of graphing with our oblique and slant asymptotes. Big idea is remember that you are dividing, and you got to use your long division in order to do it, and that our quotient gives us the equation for our oblique asymptote.